All right, today we are covering second to last section of chapter 6. We will still have 6.7. For 6.6, we are going to use proportionality theorem. So we're still just working with proportions in triangles. Some of them will be set up a little bit different today, but really we could fall back on a lot of our prior knowledge to set up proportions here. For our first warm-up, give the postulate theorem that justifies why the triangles are similar. Taylor? Angle is our natural choice, partially because we weren't given any sides. Angle similarity. We've got those 80-degree angles, and then the angle at the top would be in common, bless you, for both triangles. So by the reflexive property, it would be congruent to itself. We may not know what the angle measures are, but we do know that they're congruent. Questions about number 1? Kobe, you with us? Kobe? Let's look alive. That means like sitting up. Sit up. Look like you're paying attention. Okay. Number 2, we have to solve that proportion. To solve proportions, we cross multiply. So 16x equals 32 times 12 minus x. You could make this a little bit easier on yourself from the beginning by dividing by 16. You don't have to do it this way. I just think it makes it a little easier to do your distributing. So then you're just taking 2 times 12 instead of 32 times 12. But either way you do it, you should be getting the same answer of x equals 8. After we divide, I'm running out of space. We all get x equals 8? If we didn't, do we have questions? If you distributed the 32 and then ended up combining like terms and dividing by a bigger number later, that's fine. But no matter how you did it, you should have gotten x equals 8.
Could you also simplified or something before you did the cross multiply?
Yeah, you could have simplified the fraction 16 over 32 before you even cross multiplied. That's another option. Questions, concerns about warm-up number 2? Okay, on we go. The triangle proportionality theorem states that if a line parallel to one side of a triangle intersects the other two sides, then it divides the sides proportionally. Now, at least in this diagram and maybe on the one on your page, these little parallel triangles that they put are awfully small. So if you want to make them a little bit bigger to see that those are parallel, you could do that. So this line BE is parallel to CD. And it intersects the other sides, AC and AD, of that triangle. Because of that, it divides the sides proportionally, meaning that if we compare the two pieces that it creates on top, so CB compared to BA, that ratio is equal to DE compared to EA. Of course, from this, we could come up with other equivalent statements, other equivalent proportions. But this is the basis of it. So here, instead of talking about one triangle to another triangle, we're more talking about one part compared to the other part of the same side. and then one part compared to the other part of the same side. Now, since I started on the left side of the triangle when I was on the top, I had to start with the left side when I moved the left part of that side at the bottom. Might make more sense when we have numbers in there. Why we can't just mix and match. Have to be consistent. Questions about the triangle proportionality theorem? Okay. Then we can state the converse of it. If a line divides two sides of a triangle proportionally, then it is parallel to the third side or other side. So this time it goes a little bit differently. If CB over BA is equal to DE over EA, if that's true, then we can conclude that CD is parallel to BE. Whereas in the other one, we started off knowing that they were parallel. Remember that the converse just means we switch the hypothesis and the conclusion. So we're just going the other way. If you know they're parallel, then you know they're proportional. If you know they're proportional, then you know they're parallel. Questions, concerns, need more time. Okay, these shouldn't be too bad to use because we've been doing lots and lots with proportions. In the diagram, QS is parallel to UT. They marked that for us. I'll relabel that T down there. Again, if you want to make those triangles a little bit bigger, bolder, you can. We know that those are parallel, so we would know that the sides are divided proportionally. They tell us that RQ is 10, RS is 12, and ST is 6. We are asked to find QU. So if we don't know something and we want to find it, we could label it with X or some other variable. Again, like with many problems we've done with proportions, there are many correct possibilities for setting this up. If I want to start my first ratio with X, what do you think I need to compare it to based on the theorem we just did on the front? X over 10. So I'm not saying this is the only correct possibility. It would be possible to compare it to 6 and still end up with the right answer. But if we go kind of by the book on this, we're comparing one piece to the other piece of the same side. I'm not saying it's not possible to get the right answer doing it a different way. This is just the way I'm sticking with for the notes. So I compare the little piece to the bigger piece of the same side. What do you think my other ratio needs to be? Good, 6 over 12. We should be pretty good at cross multiplying at this point and solving one-step equations. We get that X equals 5. Well, so it wasn't necessarily just X we wanted. They wanted us to call it QU. If you were to leave it as X, that'd be fine because we labeled it over here. What if they'd asked us for RU instead? Okay, we would have done it the same way. You just would have had to add the 10 on the end and gotten a 15. Questions, concerns? Need more time? Okay, like I said, these should go pretty quick because we've done so many proportions. Same kind of problem. We were given parallel lines, therefore we know our sides are divided proportionally. I'll label what they told us in the directions. RP is 12. We're trying to find MR, so that's what I'll label with an X. Who wants to tell me the proportion they set up?
X
Akira?
over 12
Oh.
equals 15 over 20.
Okay, so that's, well, Akira had raised her hand, but I suppose that we'll just give Akira a turn another time. Okay, this would be one correct way to set it up. This is not the only correct way, but it's a good one. We cross multiply. 20x equals 12 times 15. If you want to go ahead and get that product, that's fine. Since I'm standing over here without a calculator, I'm going to make the mental math a little bit easier on myself. Either way, we should all get an answer of 9. So MR would have a length of 9. Yes, when you set this up, if you'd wanted to reduce 15 over 20 first, that would have been fine. You could do that. You need to be showing me your original proportion, and you need to show me some of your steps to solve it. Like, show me your cross products. If you don't show me divide by 20, I can live with that. But I better see your original proportion and your cross products, and then your answer. Questions, concerns about what I expect? Questions, concerns about how we did the problem? Alrighty then, on we go. If 3 parallel lines intersect 2 transversals, then they divide the transversals proportionally. Okay, so again, if you want to make the statement, you can. If RS parallel to WJ parallel to NP, then, and it's much like what we were just doing, it's just not quite in the shape of a triangle. So then RW compared to WN is equal to SJ compared to JP. Notice we're still taking pieces of one side compared to each other equal to pieces of the other side compared to each other. Same idea, just not in a triangle. Again, multiple correct possibilities for setting up the proportionality statement. Who needs more time with it? Going once. Twice. Okay. On example 3, we're asked to find the length of AB. Again, if we don't know something, we generally label it with a variable. If you want to keep using X, that's fine. If you want to use a different variable, that's fine. Who would like to raise their hand and tell me the proportion that they set up? Batea?
24 over 37. Is equal to 27 over A.
Good. Again, this is not the only correct option, but it's a good one, so we'll use it. So 24x equals 32 times 27. Divide both sides by 24. I'm going to make it a little easier on myself. Do 8 times 3. No matter how you do it, you should get x equals 36. AB is equal to 36. Now, when you do problems like this, and I could have mentioned this before, you should be able to kind of check the reasonableness of your answer. How does 24 compare to 32? 24 is... How does it compare? Smaller, okay, less than. 24 is smaller than 32. So we would expect 27 to be smaller than whatever we get for AB. Does this make sense? Okay, so if we had gotten something like, I don't know, 20 for X, we should be able to see right away that doesn't seem right. Okay, so you can kind of do a little self-check. Like 36 is bigger than 27. Okay, that seems reasonable. Questions on example 3? Okay, we'll keep it going. If a ray bisects an angle of a triangle, then it divides the opposite side into segments whose lengths are proportional to the lengths of the other two sides. Now, in my personal opinion, the wordiness of this gets to be a smidgen overwhelming. But we'll break it down. If ray CD bisects, what does it mean to bisect? Split it into two congruent parts. Bisects angle ACB. If that happens, then there are, again, multiple possibilities for how to set this up. But it splits this third side into proportional pieces to the other two sides. So one way we could set it up would be to compare AD to AC. And that would be equal to DB compared to BC. Again, not the only possibility, but it's one of them. Another possibility would be to compare those two pieces together. So AD to DB equal to AC to BC. Again, if we just switched the AC and the DB, we switched the means. That's one of our ways of creating equivalent proportions. So however you want to think about it. I kind of like to think about it as like this little triangle compared to this little triangle. Either way is fine with me, as long as you show me the proportion you're setting up. Questions about this theorem? Need more time to get it written down. We'll move on to our last example. Find the length of DG. Okay, if we don't know something, we usually assign it a variable like x, so we could put an x by DG. So we could start setting this up. We could compare x to that 8, the side next to it. But when we go to set up our other ratio, we run into a little bit of an issue because they didn't tell us this other piece GF. Ari, what could we do about that? Good. Instead of using another variable, because that wouldn't be helpful, we can use what we know and say if this piece of it is x and the whole thing is 14, then this one must be 14 minus that x. So 14 minus x goes over the 12. Okay, cross multiply. Make sure you're showing me your cross products. Make sure that you are distributing that 8. If you don't, this is not going to go well. 8 times 14 gives me 112. Minus 8x. Add 8x on both sides. Divide. This one doesn't come out super nice, but it's also not super ugly. 5.6. So the length of DG is 5.6. What if I wanted the length of GF? Okay, we'd subtract it from the 14. What do we get? 8.4. Okay, and you could always double check yourself real quick on these ones as well. If you were to take 5.6 divided by 8.4 in your calculator, it should be the same thing as 8 divided by 12, or any of those other ratios that we could check. Okay, notes today, pretty short, sweet, and simple. Even though we had new theorems, the work involved is not a whole lot different from what we've been doing. Questions, concerns? Needing more time? Okay, so your homework should be on your assignment guide as well. Looking ahead at our assignment guide, just briefly, the plan, assuming, weather cooperates, is that tomorrow we would review, and that means on Friday we would have a quiz. Okay, and then next week we're looking at doing our last section on Monday, reviewing Tuesday, test on Wednesday. Obviously, if the weather interferes, that schedule will get pushed back. So right now we should be preparing for a quiz on Friday.